Okay, in the previous lecture, we have learned um, the four different types of operations for vectors. Actually, in this lecture, we're going to learn the same thing for the four different types of operations for vectors, but in a different form, which is component form. So in the previous lectures, what we have learned for each vector is called abstract form. In abstract form, let's say if you have vector A, you don't have any uh, coordinate system or reference. It's just vector A. That's called abstract form. But in a lot of cases, a more useful form of your vector is called component form. That means you put your vector into coordinates, for example, x, y, z coordinates or Cartesian coordinates. And then we do calculations in the x, y, z components. Okay, now, first let's see how to put a vector into a XYZ system or Cartesian coordinate system. So first, if you have vector A, you can always choose a starting point of your vector A to be the origin of your XYZ components. For example, you can put it here, and here is your XYZ origin. And then you can project your vector A into x direction, y direction, and z direction in x and y, z coordinates. And then you will have your, let's say, ax in x direction, ay in y direction, az in z direction. Here, x hat means x direction. It's called the unit vector, which means the magnitude of this vector is 1, but the direction is in x direction. The same thing for y and z unit vector. So this is vector components. An arbitrary vector A in abstract form can always be expanded or decomposed in terms of basis vectors or component format of vectors in this way. And it could be written in A equals to AX, which is the magnitude of the vector A in X direction times the direction of X plus AY, Y hat plus AZ, Z hat. So AX, AY, AZ, they are components of the vector. Geometrically, there's a projections of A along three coordinates, and AX could be calculated by the vector A dot X hat. AY equals to A dot Y hat and AZ. We can now reformulate each of the four vector operations previously into a different rule in the component form. Let's do it one by one. So number one operation, adding two vectors, A plus B. So in component form, you can write A into this format, and you can write vector B into this component form. And then this is x hat, this is x hat. You can combine them. You have ax plus bx times x hat. The same thing for b hat, z hat. So this is a way of calculating a plus b. So the rule number one, to add vectors, you add components. Okay, now let's see the second operation, which is scalar operation, a scalar product. So let's say if you have a vector A and you use a scalar, which is small letter a, product your vector A, due to the distributive feature of scalar product, you can distribute A or the scalar into its components. You will have A dot AX, X hat plus Y and Z directions. So this is based on its how to write it? This tree. Oh, there's something wrong with the pen. Difficult to write. Distributive. This is due to the distributive feature. It's very difficult to write a letter on my iPad. Okay. So that's the rule number one. Number two, sorry. To multiply by a vector, you can multiply each component by this vector due to the distributive rule. Okay, now let's see the third operation, which is cross product. Remember that, dot product. Remember that when you do a dot product, for example, A dot B, you have the equation of A dot B times cosine theta. Theta is the angle between A and B. And here, A, B, they are the magnitude of the vector A and B. So finally, you get a scalar. If you keep this in mind, now let's see, first let's see the unit vectors dot product. X dot X equals to 1 because X is parallel to itself. So theta is 0, cosine theta is 1. And the magnitude of X hat is 1 because it's unit vector. The magnitude of unit vector is always 1. So you will have X dot X using this equation. It's magnitude of X dot magnitude of X dot cosine theta or cosine 0 or 1. So finally you get 1. And X dot Y equals to 0 because the angle between X and Y is 90 degrees. They are perpendicular to each other. So you have 0 for X dot Y and also for X dot Z, Y dot Z. And then if you use A dot B, you can write them into component form. A is shown here, B is here. So let's expand it in terms. First, if you expand it, if you use AX x hat times BX x height, the x hat dot x hat equals to 1 as we shown here. X dot x hat 1. So it finally, this term multiplied by this term or dot this term, you have AX BX. If you use AX dot BY, what happens? Because this is X hat, this is Y hat, you have X dot Y hat, you have 0. So this term is 0. So if you do it one by one, you have totally 9 terms and 6 of them are 0. Only 3 terms are non-zero, which is shown here, AXBX plus AYBY plus AZBZ. So that's the rule of A dot B. Rule number 3. To calculate the dot product, multiply like components and then add them together. In particular, if you have A dot A, because A is perpendicular to itself, so you will have AX squared plus AY squared plus AZ squared. Or you just replace this A, actually you replace this B from here by A and use this equation, you will have the same thing. And the magnitude of A equals the square root of AS squared plus AY squared plus AZ squared. That's dot product. Now let's see cross product. So before we go to the cross product, let's first do a review what is product, how to do the product, cross product. So if you use A cross B, you will have magnitude of A times B times sine theta. Theta is the angle between A and B times a direction. This is the unit vector of the direction of A cross B. This direction could be calculated by right-hand rule. For example, if you have A here, B here, then A cross B will be in the direction of C. This is calculated by the right-hand rule. Okay, the same thing for X, Y, Z directions, or the unit vectors of X, Y, Z directions. Now, if you use the unit vector X cross unit vector X, what happens is you get 0 because sine theta is 0 because X is a parallel to itself. So theta is 0, sine theta is 0, so the cross product is 0. If you use X cross Y, you will have a Z. But if you use Y cross X, you will have negative Z. Same thing here. A cross B result in C, it's going up. But if you use B cross A, it results in a negative C, which is going down based on your right-hand rule. So this is X cross Y equals to negative Y cross X equals to Z. And similar things are shown below. So therefore, if you use A cross B, you will write them into component format. And then this is the component format for B. And then A cross B equals to a complicated format. It's difficult to remember. Maybe either way to remember it or more neatly is shown here. A cross B equals to the determinant of x, y, z hat, ax, ay, az, bx, by, bz. This is rule number 4. To calculate the cross product, form the determinant whose first row is x, y, z, second row is a, of course in component form, and the third row or last row is b in component form. Then you have the cross product of a and b. Okay, so far we have learned the 4 different operations for vectors in both abstract form and component form. And then let's use them to do some calculations or just apply it in some interesting examples. Let's see this example. Find the angle between face diagonals of a cube. Okay, let's see the picture. If you have a cube here and you have diagonal on the surface of XZ panel, which is shown in this vector A, and another diagonal, which is B in Y and Z panel, what is the theta between, what is the angle between A and B? You will have different ways to solve the angle between A and B, but in the textbook, it gives you one way. Let's first go through the method introduced by the textbook. It's a practice for vector operations. So first, let's write down A and B in component form. If we define x, y, z coordinates and the origin is set to be here, then A is 1, 0, 1 because it's in X and Z panel. And B is 0, 1, 1 because B is in the Y and Z panel. Does that make sense? Okay, now you have A and B vectors. Let's do a product of A and B. A dot B equals to, here is A and here is B. You can use the dot product rule, which is A dot B equals to AX dot BX plus AY times BY plus AZ times BZ. So finally, this is A and this is B. If you use the rule, you will have 1 times 0 plus 0 times 1 plus 1 times 1. Finally, it's 1. So this is the calculation using the component form. You can use the different way, which is abstract form. If we use abstract form to calculate the A dot B, you will have A dot B equals to AB cosine theta. And the magnitude of A is square root of 2, because this is 1, this is 1. You will have A to be square root of 2. The same thing for B, square root of 2. So you have square root of 2 times square root of 2 times cosine theta, which is 2 times cosine theta. And you know 2 times cosine theta equals to 1 because there are simply different ways of calculating A dot B. They should equal to each other. So 2 times cosine theta equals to 1. So cosine theta equals to 1/2 or 0.5. Then theta should be 60 degrees. So that's an interesting way of solving the problem. By calculating A dot B in two different ways, you get the value of theta. That's quite interesting. Another way to solve the problem perhaps is even easier. You have A here, B here. Let's connect A and B. Connect the tip of A and B. You will have another diagonal, which is, let's say it's C. Now, if you look at the triangle of A, B, and C, so let's say this is A, this is B, and this is C. You'll figure out in this triangle, in this ABC triangle or ABC triangle, I write it here, you'll figure out they have the same length. They're all square root of 2. So it's a equilateral triangle. For such a triangle, the lengths are the same and the angles are the same. And the angles equals to 60 degrees. That's a feature of this equilateral triangle. So by using this geometric way, you can also figure out that the angle between A and B, A and C, B and C, they are all 60 degrees. So using this way, you can also solve the problem. Okay, anyway, maybe you have more different ways to solve this problem, but in the textbook, it just wants you to practice the dot product in different form, component form and abstract form. Okay, triple product. For triple product, we're not going to introduce the details here because we don't use it, those features quite frequently. When we need to use them in future lectures, I'll go back to here to introduce it one more time. But now let's just go through it quickly. For triple product simply means you have 3 vectors and you do some product. For example, B cross C first and then dot B cross C. And then it has some features. It has some features. Oh, sorry. It has some features, which is shown here. Or if you have 3 vectors cross each other, first B cross C and then A cross B and C, it could be expanded using the so-called BAC-CAB rule, which is if you use A cross the cross product of B and C, then it could be written in B dot A dot C subtracted by C dot A dot B. Yeah, that's a little bit too complicated. Let's introduce it in the future when we really need to use it, because if you don't use it, I'm almost sure you won't be able to remember it or understand it. Another important topic is position, displacement, and that separation vectors. That's more useful. Um, okay, so previously, we always introduce vectors, and a vector is an arrow. But here, let's say a location of a point in 3 dimensions can also be described by listing its Cartesian coordinates. The vector to that point from origin is called its position vector. Okay, so for example, in the past, we use a vector to indicate, um, let's say, an arrow or a connection between one point to another point. But in the future, we can always use a vector to indicate just a single point or location, which is, for example, here. So the location or coordinates of this point is xyz. So the vector of this location could be the vector starting from the original point to its location, which is shown here. So we can use xyz to stand for a vector like that, or a location of this point. This is called a location vector or position vector. That means a vector from origin to that point. And we can define r equals to x plus y plus z components. Okay, so because letter R for the position, then the vector stand for the arrow from origin to this position. And the magnitude of R, of course, equals to square root of x squared plus y squared plus z squared. It is the distance from the origin to the position of your concerned position. And the direction of R, or the unit vector of R, could be calculated by using R over its own magnitude. So the vector is shown here and the magnitude is shown here. It's a normalization. So by using this R over R, you will normalize your vector to a magnitude 1 vector and keep the same direction. So it's a unit vector pointing radially outward. Okay. Let me see how to put. And the infinitesimal displacement vector from x, y, z to x plus dx, y plus dy, z plus dz vector could be described by dl equals to dx times x direction, dy times y direction, dz times z direction. Of course, we can use dr because this is infinitesimal for r. So generally we should use dr actually, but because we use dr so many times in the future, so we just call, or we just define a special notation here, dl, to stand for dr. They're the same thing actually. So in the future, if you see dl or dr, by default, they are the same thing. That's the infinitesimal displacement vector of r. Okay. So in our course, one frequently encounters problems involving 2 points, typically a source point, which is r prime, where electric charge is located, and then a field point. let's say you have a coordinates. It should be in 3-dimensional, but I would just make a 2-dimensional coordinates for simplify. So you may have vector or point here. Let's say it's r prime, which is, let's say, a charge. And sometimes you want to calculate the field at another position. Let's say this is r. Then you want to calculate the field generated by this charge here. Then quite frequently, we involve 2 points in electrodynamics, which is charge position and field position. Okay. Then in this case, in quite frequently, we let me see. We use a separation vector from the source point to the field point, which is r subtracted by r prime. And then you will get a new vector from here to there. And we use a script letter r to stand for r subtracted by r prime. And the magnitude, of course, is the magnitude of r subtracted by r prime. And the unit vector could be written in this way. The r hat equals to vector r over magnitude of r. And this r, or the separation vector, is written in this way. Okay, nothing special. In Cartesian coordinates, it could be right in this format, and the magnitude of this separation r is in this way, and the unit vector of this separation vector could be written in this way. Okay, so that's all for today's class. We have introduced something more than the abstract vectors. Okay, let's stop here. I'll see you in next time. Let me see how to stop it.